Hey everyone, today we're going to be talking about the dot product of two vectors. Just like vectors can be added and subtracted, which we can show through tip-to-tail addition. So if we had vector v and vector w just like this would be this vector sum, v plus w. They can also be subtracted. So if we went ahead and took those same vectors, we had vector v, vector w, and this resultant vector would be v minus w. Just like vector addition and vector subtraction exist, vector multiplication also exists. But there are two types of vector multiplication. There's the dot product and the cross product. In this video, we're going to be getting into the dot product, which is also known as the scalar product. So, the definition of the dot product is that let's say we were given two vectors, vector A, which was notated by its components a1, a2, and a3. And then we had vector B, notated by its components b1, b2, and b3. To find the dot product, or a dot b, what we're going to do is you're going to multiply the respective components together and sum all those products up. In other words, what you're going to see is you're going to see a1 times b1 plus a2 times b2 plus a3 times b3. This right here is the definition of the dot product. And you can use this definition to prove all sorts of theorems, or all sorts of properties, should I say. We're going to get into the theorem that we're going to get into. We're not going to do the proof for because it's a bit complicated, but there is a theorem that you can use this definition for. So, some properties, for example, let's say we're going to multiply a vector A that looked exactly like this, just a1, a2, a3 by itself. We get a1 times a1 plus a2 times a2 plus a3 times a3, and that works out to be a1 squared plus a2 squared plus a3 squared. Now if you notice here, the sum of the squares of all the components, this is the same thing as the magnitude of a squared. Hence, we get that the dot product of a vector in itself is just going to be the magnitude of that vector squared. That's just an example of a property. Some other properties include the zero vector. So 0 dotted with a vector is going to give you 0. If you were to do a scalar multiple, so CA times B, CA dot B, this is the same thing as A dot CB. And there's even the commutative property of dot products, where A dot B is equal to B dot A. There are several other properties out there, but for time's sake, I'm not going to get into them, but you're free to discover them if you wish. So what can we actually use the dot product for? That's the question. So this is the theorem I was talking about, or foreshadowing it a little bit earlier. So the theorem for the dot product states that if you have two vectors here, A and B, we're just going to roll with these examples here. This is going to be equal to the magnitude of A times the magnitude of B times the cosine of theta, but theta is the angle between A and B. So I should probably specify, we're not going to be using these vectors here. We can only use two-dimensional vectors, because two-dimensional vectors only have one angle theta between them, so there's no room for ambiguity. So, let's say we had two vectors here, A and B, that looked like this, and we had this angle theta. By looking at this formula, we can actually use the dot product to find the angle theta between the vectors. And we can also find out if the angle is acute, obtuse, or a right angle. In other words, if the vectors are perpendicular or not. So, let's go ahead and take a look at this formula right here. Let's say we were to need to find theta. We knew how to find the dot product because of the components, and we knew the magnitudes because, again, components. What we can do here is we can take this formula and say that cosine of theta is equal to A dot B divided by the magnitude of A times the magnitude of B. And now to find theta from this, we can get that theta is simply the inverse cosine of A dot B divided by the magnitude of A and B. So let's just try a quick example here, just to get ourselves accustomed to this idea. So let's let vector A and we're going to use unit vector notation here. So let's let vector A be I plus 4j, and let's let vector B be equal to 2i minus 3j. And these i and j's here, they represent the unit vectors in the x and y direction respectively. So we can go ahead and rewrite this for more concise notation. So we have 1i plus 4j for vector A, and then for vector B, we have 2i minus 3j. So to find what cosine theta is, because we can't find what theta is without a calculator, possibly, to find what cosine theta is, we can just do the dot product of these two vectors and then divide them by the product of the magnitudes. So let's go ahead and do that. So cosine theta is a dot b divided by magnitude of A, magnitude of B, and this is going to be equal to 1 times 2, so this is the dot product component-wise multiplication, 1 times 2 plus 4 times negative 3. And this is going to be divided by the magnitude of A, which is the square root of 1 squared plus 4 squared, so that's going to be the square root of 17, and the magnitude of B, which is the square root of 2 squared plus negative 3 squared, so that's going to be square root of 4 plus 9, which is root 13. So I'm just going to leave it in this form and say that theta is the cosine inverse of 1 times 2 minus 12, which is going to be negative 10, divided by the square root. I can't do the mental math in my head, so I'm just going to say this is 17 times 13. Now, what can we do with this information? We can always plug this into a calculator, but let's say you're not given a calculator and you want to make use of this information. Here's the thing. If we have a negative value inside this cosine inverse function right here, if this value is less than 0, then that means that you're going to get an angle measurement between 90 degrees and 180 degrees. Why? Because the cosine of every angle between those two values is always going to be negative. You can even check that with the unit circle, because if we go ahead and draw that, you can go ahead and focus on quadrant 2, or the values between 90 degrees, 180 degrees. You notice here, the x component of every angle, or the x values, they're always going to be negative. Hence, cosine inverse is going to spit out a value between 90 degrees and 180 degrees. And any angle between 90 degrees and 180 degrees is obtuse. So we can say that theta, in this case, is obtuse. So that's just one way we can use the dot product. Another way we can use the dot product is to actually find vector components of some vector relative to another vector. In other words, the vector projections of one vector onto another. So let's go ahead and try an example here. So let's go ahead and say we had this vector here and this vector here. Let's call this vector A and let's call this vector B. And we know here we have our angle theta. So if we were to go ahead and sort of turn this vector A into a right triangle with this angle theta. So when we do that, we have a right angle here, and we can use trig, we can just use basic trig to identify that this vertical component is the magnitude of A times sine theta and the magnitude of A times cosine theta. Let's focus more on this cosine theta, because what we're really trying to go for here is how much of vector A lies on vector B. And that's what this A cosine theta here represents. The magnitude of A times cosine theta is going to give what's known as the scalar projection of A onto B. But what can we do with this A cosine theta? Let's say you're not even given anything about theta. Let's say you only know the components of A and B. Well, there's an easy fix for that. So you know that the scalar projection, which we're going to call comp sub BA, which basically means the scalar projection of A onto B, this is going to be equal to the magnitude of A times cosine theta. But we can multiply this by the magnitude of B divided by the magnitude of B. As a result, we're going to get that this is the magnitude of A times the magnitude of B times cosine theta divided by the magnitude of B. Notice here, we have this magnitude of A, magnitude of B, cosine theta this expression is identical to the dot product of A and B. In other words, we can say the scalar projection of A onto B is equal to A dot B over the magnitude of B. Now, what can we do with this information, though? We can go ahead and use this scalar projection to sort of do a scalar multiplication in essence. So that way we can actually find the vector itself, the vector of A that lies on B. Sorry, that made no sense. The vector component of A that lies on B. In other words, the vector projection of A onto B. So to find that, let's go ahead and call this vector here P. We're going to use this scalar quantity right here, which we're going to use a P not vector. So it's going to say P, and then we're going to use this U hat. So what this U hat represents is this is the unit vector in the direction of B. If you're familiar with unit vectors, you would know that they always have a magnitude of 1. And the way to find the unit vector is the unit vector is going to be the vector itself divided by the magnitude of that vector. So we have vector B divided by the magnitude of B. So let's go ahead and use this expression and this expression to compute what the vector projection P is going to look like. So the vector projection P is going to be the scalar P right here of A dot B over magnitude of B times, I probably shouldn't use a dot for that because then that's going to get confusing, times the magnitude times the vector B divided by the magnitude of B. So we can say that the vector P, or the the vector projection of A onto B, is A dot B over the magnitude of B squared, this right here, times vector B. So this scalar quantity times vector B is going to give you the vector projection of A onto B. And this should make sense, right? Because what you're effectively doing is you're taking the scalar projection of A onto B, which basically gives you the amount of A that lies on B, and then you're multiplying it by a vector in the direction of B that has a magnitude of 1, which effectively means that you are giving this vector projection here this magnitude of the scalar projection, if that makes any sense. So this right here, this formula right here, is how you can determine what the vector projection of this vector A onto this vector B is. And that is pretty much how you can use the dot product in the context of vectors. So in the next part, we are going to get into the cross product and the versatility of the cross product. You can use it for areas, you can use it for planes. We're going to get into all sorts of that stuff. But for now, this is what you need to know for the dot product, and that concludes this video.